Hello and welcome to this fourth video in a series on calculations for National 5 Chemistry. If you haven't seen the previous ones, I do urge you to go and look at those first, particularly the number 3, because I'm going to have to assume that you know certain things and that you can do certain things. First off, I'm going to need to assume that you know that 1 mole of anything contains the same number of particles as 1 mole of anything else. And by particles there, I mean what the substance is made of. Is that molecules, atoms, ionic units, whatever? I need you to be able to convert mass into number of moles and back if you know the gram formula mass. And similarly for solutions, how to convert volumes and concentrations into numbers of moles and back. Okay, so first off though, we need to talk about balanced equations. Okay, let's consider this reaction here. Copper can be extracted from copper 2 oxide by heating it with carbon. The other product is carbon dioxide. So let's write down an equation. There we are. CuO, because the valency of copper here is 2 and the valency of oxygen is 2, so they cancel down. Carbon is just C, it's an element, so you just write the symbol. Copper 2 is an element, so you just write the symbol. And carbon dioxide there is CO2. But there's a problem with this equation as it stands. You've got 2 oxygens there on the right hand side, but over here the only oxygen is there and there's only 1 of them. So we need to balance this equation up by putting a 2 there. That gives me now 2 coppers and 2 oxygens. But I've now got 2 coppers, but I've only got 1 over here, so I need to put a 2 there as well. And that equation is now balanced. I've got 2 coppers on the left, 2 coppers on the right, 2 oxygens on the left, 2 oxygens on the right, and a carbon on each side. Okay, so let's see, what does that equation actually mean? Naively, we might think it means this, that 2 molecules of copper oxide react with 1 atom of carbon to produce 2 atoms of copper and 1 molecule of carbon dioxide. See those inverted commas though? We don't actually get molecules of copper oxide. They come in kind of ion pairs, a copper ion and an oxide ion. But more than that, we'll see that this is not particularly useful. Before we get rid of it though, let's consider that we could just scale it up. This could also mean that 200 molecules of copper oxide react with 100 atoms of carbon to produce 200 atoms of copper and 100 molecules of carbon dioxide. All I'm doing is scaling up. I could do that for any number. Okay, but what we're going to find particularly useful is to say, okay, we can make that moles, right? We could say that 2 moles of copper oxide react with 1 mole of carbon to produce 2 moles of copper and 1 mole of carbon dioxide. That's going to turn out to be much more useful and correct. Okay, let's see what we can do with that. I'm going to start with a calculation using the masses of things. We'll leave solutions for a moment. Okay, let's consider this. What mass of carbon dioxide is produced when 7.95 grams of copper 2 oxide react with carbon? Okay, now here's our equation. We saw that a moment ago. Now, in that question, I'm told something about the copper oxide. I'm told how much of it there is. Okay, and I'm asked about the carbon dioxide. Okay? Right, let's work out some formula masses, because that's the way we roll. Okay, in copper oxide, I've got 1 oxygen. That's 1 lot of 16 is 16. I have 1 copper. So that's 1 lot of 63.5 is 63.5. That means the gram formula mass of copper oxide is 79.5. Okay, carbon dioxide. Now I've got 2 oxygens in there. So that's 2 lots of 16 is 32. I've got 1 carbon. That's 1 lot of 12 is 12. So the gram formula mass of carbon dioxide is 44. Okay. Now then, I'm told here about the copper oxide. I'm told I've got 7.95 grams of it. I now know both the mass and the gram formula mass for copper oxide. That means I can go ahead and work out the number of moles using that nifty triangle that we looked at last time. And I see that the number of moles is the mass divided by the gram formula mass. Okay, so that's 7.95, I get that from the question, divided by 79.5, that's the gram formula mass we worked out on the right. Okay, and that comes out as 0.1. Okay, the numbers won't always be quite that simple. I've kept them simple here to make understanding what's going on a bit easier. Now, if we look at the equation, the ratio of copper oxide to carbon dioxide is 2 to 1. So however many moles of copper oxide I start with, I'll wind up with half that number of moles of carbon dioxide. Okay? That's that ratio there, 1 to 0.5. Notice, by the way, this is why using moles rather than atoms and molecules is better. You can easily have 0.1 of a mole or 0.5 of a mole. You can't reasonably have 0.1 of a molecule or 0.5 of an atom. That wouldn't make any sense. Okay, so I know I'm going to finish up with half the number of moles of carbon dioxide as I started with copper oxide. So I'm going to wind up with 0.05 moles. I started with 0.1 moles of copper oxide. I wind up with half that number of moles of carbon dioxide. That's 0.05. Now I'm on the home stretch. I now know how many moles of carbon dioxide I've got. I know the gram formula mass of carbon dioxide, and according to the magic triangle at the bottom, I need to multiply those together. So the mass of carbon dioxide is 0.05 times 44. The number of moles times the gram formula mass, and that comes out as 2.2 grams. Okay. I'm going to give you a moment there just to look over that working again. Okay, moving on now to solutions. Remember, solutions are different because you've got water in there as well as the substances you're dealing with, so we have to talk in terms of volume and concentration. Okay, so here's the example I'm going to use this time. What is the concentration of a sodium hydroxide solution if 10 millilitres of it exactly neutralises 5 millilitres of 0.1 mole per litre sulfuric acid? Okay, as always, we need an equation. There are the formulas, but that's not balanced. I've got 1 sodium on the left, I've got 2 on the right. Okay, so I put a 2 there and a 2 in front of the water. That should now work. Right, let's now do the calculation. I'm asked here about sodium hydroxide. And I'm told about the sulfuric acid. In other words, I'm told some information about the sulfuric acid I can do some work with. Okay. This is the magic triangle we're going to need this time. Notice it involves volumes and concentrations. Right, so let's note those down. The volume of sodium hydroxide is 10 millilitres. The concentration we don't know. That's what we're asked about. The volume of sulfuric acid is 5 millilitres. And the concentration is 0.1 moles per litre. Okay, so let's now work out the number of moles of sulfuric acid I've got, because that's what I'm told about. I've got the information I need to work that out. Okay, so my number of moles of sulfuric acid is 5 times 0.1. Now, you might want to shout out there, wait a minute, in the last video you insisted that the volume had to be in litres. And yes, if the final answer I want is to know the number of moles, that's what I'd have to do. I'd have to make the volume 0.005. But park that thought for a moment, okay? And just imagine for a moment that instead of millilitres there, it says litres, okay? You'll see why this works in a moment, I hope. Okay, so I've worked out the number of moles of sulfuric acid at 0.5. Okay, absolutely, of course, it's really 0.005, but we'll worry about that in a moment. Okay, so the ratio of moles of sodium hydroxide to sulfuric acid, according to the equation, is 2 to 1. So the number of moles of sodium hydroxide I need is twice as many as the number of moles of sulfuric acid. Okay, so if I've got 0.5 moles of sulfuric acid, I will need 1 mole of sodium hydroxide. That's what the equation is telling me. The number of moles of sodium hydroxide is twice as many as the number of moles of sulfuric acid. Okay, now notice here, the thing is, this is a ratio. Okay, that's what I'm dealing with, a ratio of number of moles of one thing to the number of moles of another. Okay, that's why we don't need to worry too much about the litres thing here. Okay, it would mean dividing both of them by 1,000, and that would just sort of come out in the wash. So for this type of calculation, we don't need to worry about it. Okay, so a concentration of sodium hydroxide then is the number of moles divided by the volume, is 1 divided by 10, is 0.1 moles per litre. Okay? If you're still worried about the whole using litres thing, just think what I'd have to do there is divide by 1,000 to get it into litres, and then multiply by 1,000 again at the end to get back into millilitres. So the two things would cancel out. Okay, so there's my answer, 0.1 moles per litre. As always, practice, practice, practice. That's what really gets you home and dry on these types of calculation. The more of them you do, the easier it'll get. Okay, to finish up, you have to have a balanced equation, so make sure you've got that. Then you convert the substance you're given enough information on to moles. So in a mass question, it's the one you're given the mass of. In a solutions question, it's the one where you've got both the concentration and the volume, because these are the things you need to convert to moles. So when you've converted the mass or volume or whatever of the substance you're told about into moles, you use the equation to work out the number of moles of the substance you're asked about. Okay? And remember, that's a kind of ratio thing. Finally, you convert back to mass, volume or concentration, whatever the substance implies. Okay, so as I say, do practice these. Getting familiar with converting between mass, number of moles, volume, concentration, number of moles, it will get so much easier the more you do. Okay, thanks for watching and bye just now.